Hey, good afternoon, everyone. Let's get started. So, in the last lecture, we talked about the framework of the global variational inference, right? So, we set our goal to estimate the posterior distribution of some latent random variable given data. I suppose you got a latent variable z, and you observe some data x, right? So, you got a joint distribution of x and z, which can be decomposed as p of z prior times likelihood, right? You want to estimate the posterior distribution of z given x, right? So as we mentioned, if you just apply Bayes' rule to compute the exact posterior, in most cases, right, except like simple models like Bayesian linear regression or Gaussian mixture model, in most cases, this is infeasible to compute, right? So the idea of the variational inference is to approximate this guy with some distribution that has a simple form like a Gaussian, right? Or like other exponential family distribution. Right? Then the idea is that, okay, suppose this is my ground truth posterior, which because of the intractability, we even do not know what's the form of that, right? So we want to approximate with a simple form, a distribution with simple form, right? Like a Gaussian distribution. So that represents a family of distributions. So our goal is to find out the best one in this approximation family that is closest to the ground truth, right? That's the idea, right? And of course, the larger the family you set, then probably the closer, the best approximate distribution is to the exact posterior, right? That is the trade-off. So then there comes a problem, right? So how do we measure the closeness between your approximate distribution and your true posterior, right? So we can use the KL divergence, right? So want to minimize the KL divergence from your approximate distribution, right, to the true posterior, right? And you want to find out a member in your approximation family which minimizes this KL divergence. You use that as your best approximation in a given approximation family, right? But there's a problem, right? You cannot directly compute this KL divergence because you need to compute the exact posterior, right? If you are able to compute the exact posterior, why do you need to approximate? Right? So in practice, you have to avoid explicitly minimizing this KL divergence. So the key observation in the variational inference framework is that, okay, from what we have derived in the EM algorithm, right? If you look at the log model evidence, which means that if you marginalize out the latent random variable z in the joint distribution, you only get the marginal distribution of the data x, take a logarithm, which is called evidence, right? If you apply the Jensen's equality, which we discussed in the EM algorithm, you can decompose this model evidence as two terms. One term is a lower bound. The other term is the KL divergence, right? Because the evidence, if you assume any hyperparameters of interest are fixed and known, right? The evidence is a constant, right? It won't change. And it is equal to this lower bound plus the KL divergence, right? Because KL divergence is always non-negative, that means this lower bound is always a lower bound, right? So that means if you maximize the lower bound, it is equivalent to minimizing the KL divergence. So instead of explicitly minimizing the KL divergence, we can maximize the evidence lower bound to find out the best approximate distribution Q of Z. If you look at the form of the evidence lower bound, we find that it is an integral of the approximate distribution Q of Z times the log fraction between the joint distribution of X and Z and Q of Z itself, right? Because Q of Z also is often having some kind of simple form like Gaussian distribution. So, and then the P of X Z, right? We cannot compute P of Z given X, but it's very easy to write down and compute the joint distribution of P on X and Z. It's just you just multiply the prior of Z and likelihood of X and Z. So compared with the Carrier divergence, this lower bound is often much easier to compute and optimize. So that's our idea, right? The global variation inference. We want to maximize a variational evidence lower bound explicitly, which is equivalent to implicitly minimizing the Carrier divergence from the approximate distribution to the true posterior. Then the remaining question would be, okay, how do we choose the form of Q of Z, right? In other words, how do you choose the approximation family where Q of Z belongs to, right? Stays in. Right? And there is always some kind of trade-off, like the larger family of approximation distribution you choose, the more difficult or more costly you maximize this variational evidence lower bound. The simpler form you choose, the simpler form you choose of this Q of Z, the easier for the optimization and computation, but the worse the approximation quality. Right. So any question? We got a quick review of the variation inference framework we discussed in the last lecture. Everyone is on the same page, right? Okay. So for simplicity, right? So if you look at this integral, this is essentially this variational evidence lower bound, right? This is essentially also an expectation, right? It's an expectation of this log fractional under the variational approximation Q, right? Approximate distribution Q. And so sometimes we also write the evidence lower bound in terms of the expectation, notation of expectation, right? Expectation of log fraction between the joint distribution and the approximate posterior Q of Z. So next, we're going to introduce a very classical and popular variational inference algorithm. It's called a mean field variation inference. So you see that it just instantiates this global variation inference framework with a particular type of approximation family. Right? So what is that approximation family? We call it mean field approximation. So what is mean field approximation? So we assume the form of our approximate distribution is factorized over several groups of subgroups of the random variables in Z. Right? So Z can view as a set of random variables, right? In general, can view as a vector. Right? You can partition this vector into several subgroups like Z1, Z2 to Zm, something like that, right? And the mean field approximation family means that we're going to assume my posterior approximation is factorized as some posterior approximation over Z1 or Z2 over Zm. And also this Z1, Z2, Zm, they are non-overlapping. They do not overlap. In other words, we're assuming in my approximate distribution, Z1, Z2 to Zm, they are independent. Right? They're independent. Of course, this introduces some kind of like inaccuracy, right? Because in practice, maybe those variables are really, in the ground truth posterior, those variables Z1, Z2 to Zm, they're dependent, right? But here, to make this approximation, we assume they're independent. But we'll leave the flexibility that each of these Q of Zi can be actually valid distribution. We do not know the form. Does it make sense? Right. This is my specific design of the approximate posterior distribution. Right? And in many practical cases, like people assume that Z1, Z2, Z3 are all individual elements, meaning that I assume they are fully, the variables, each variable inside this Z vector are fully independent. This, of course, is kind of a pretty rough approximation. Okay? But interestingly, you see that in practice, such a rough approximation often works pretty well. So now let us look at, okay, given this form, right? Given this mean field factorized form of the approximate posterior distribution, how do we update or estimate each of this QZI? Right? That's our goal, right? We want to find out the best QZ, namely each QZI, which minimizes the Carroll divergence. In other words, maximizes the evidence lookup. Right? So we just follow the framework, right? We maximize this evidence lower bound, which is the integral of QZ. We know that QZ is factorized as the product of those QZIs, and multiply with log fractional between the joint distribution X and Z and the product of those QZIs. Right? So then the problem is that how do we maximize this guy to find out the best QZIs? Right? That's our goal. And there's no analytical solution for this. It's not like you cannot directly write down some form that give you the optimal QZIs. Right? So we're gonna use alternating updating scheme. So basically, the idea is like, okay, I need to update a set of posteriors, right? QZ1, QZ2, QZM, for example, right? So this is L function, right? So the idea is that, okay, every time I'm gonna update only one factor and fixing all the others. Like for example, at the beginning, I'm gonna fix QZ2 to QZM. I only update QZ1. And then I fix QZ1 and QZ3 and so on. I only update QZ2. And then I fix QZ1, QZ2 on the others, only updating QZ3 and so on. We'll do this cyclically and update each Q factor until convergence. Does it make sense? Right? That's the idea, right? And then let us look at how do we fulfill the particular update, right? Let us pick up arbitrary factor, say Q of ZG, right? So suppose all the other factors, namely those QZIs where I is now G, are fixed, right? We only update QZG, right? Which maximizes the evidence lookup, right? How do we find out the optimal update? So there are two ways of doing this. One is using a functional derivative, where you set functional derivative with respect to QZJ to be 0. It is fairly easy to get our updating rule. Right? So, but I'm not going to talk about that because we need to know what's the definition of the functional derivative. Right? I'm now introduce another more straightforward or easy way to look at this. Right? You see that it's very natural to get the optimal update of QZJ, given all the other QZIs fixed. So if you look at the evidence lower bound, which is only with respect to Q of ZG, right? So you find that if you look at here and here, right? If you just decompose this log fraction, it is the log joint probability subtracted by log QZG, right? So we know that all the other QZIs, which I equals where I not equal to G is constant to QZG, right? So we can just throw out all the other terms. So that means you just need to subtract this guy, right? Integral of QZJ log QZG. And then let us look at the numerator, right? So for the numerator, or because this numerator is a Joint distribution of x and over all the zj's to kind of like couple all the variables in z, right? You cannot directly throw them out, right? So in the first term, you're gonna have this integral of QZG multiplying with the product of the remaining q factors and multiplying with this log joint probability. Does it make sense? Right. This is just a straightforward derivation, right? So if we and here the integral is over the entire z, right? So you can do the integral over all z not equals to j first, right? And then in the outer level, you do integral over zg, right? Now, if you look at this integral inside, right, which is the integral that are only on z not g, what can we observe? Any thought? It's just an expectation, right? So this guy are approximate posterior of all z variables except zg, right? Then you multiply with this log joint probability. You integrate out all z variables except zg, right? So this is essentially an expectation of the log joint probability under part of the approximate posterior, right? Which is only under QZ not G. Right? Does it make sense? Any question? Okay, great. So this guy, remember this guy is still a function of ZG. Right? Because this Z contains both Z not G and ZG, right? You marginalize out Z not G, but you still leave ZG here. So this expectation is still a function of ZG. So don't get confused, right? Any questions so far? Okay. So now, look at this intermediate results, right? We want to this guy and this guy, right? We want to merge the two terms all together again. Right? Want to make it easier to deal with, right? How can I do that, right? So this guy equals to those things, right? Equals exponential of this EQ Z not J. I'm just copying down, right? X and Z, right? And then take exponential, right? I take exponential, I take logarithm. It's the same, right? So, and then because now I have log here in this integral, I have a log Q of ZG in this integral, right? I can combine, I can merge these two log terms, right? So I can make it another log fraction. So if you merge the two terms together, right, you got a QZJ logarithm, you got exponential of this EQZ not J log drawn probability. In the numerator and in the denominator, it is QZG. And of course, this integral is over ZG, right? Does it make sense? So now, what does this look like? Yeah, of course, it's expectation. But we want to connect it to some other measurement. We have just, yes, the KL divergence, right? So if you look at the general definition of KL divergence, right, we look at the KL divergence between the distribution, say, Q theta and P theta, right? It is integral of Q theta and log fractional between Q theta over P theta, right? So we know that when is the KL divergence is minimal? When Q theta is exactly the same as P of theta will be 0. In all other cases, it will be positive, right? So if we can somehow convert it into some KL divergence, but here KL divergence will be negative because you have to put QZG in the numerator, right? So let me put it a little bit change, right? If you take the minus sign from it, we're gonna switch the numerator and denominator, right? So if this guy can be a KL divergence, then you maximize this evidence lower bound is equal to minimize this KL divergence, right? And then you can just make QZG to be equal to the distribution which corresponds to the denominator. Does it make sense? It's not necessary to be. Yeah, it just has an exponential term. It doesn't mean it must be an exponential family. Right? Because for any probability density, well, you take logarithm over that and take exponential, it can still convert it into exponential form. Right? The case is that in the exponent, you should have some linear structure. Right? But here, looks like we found a way to identify which QZG should be the optimal, right? But the problem is that the denominator here is not a distribution, right? It's not guaranteed to be a distribution because it is unnormalized. So the question is, then the idea is why not just put a normalizer here? I'm not using Z. I'm using C to represent normalizer. I would claim that if you divide it by C and multiply by C, it doesn't change the optimization at all. Why? Why? Because the normalizer is constant to ZG, right? It doesn't matter, like you divide this exponential by the normalizer C and multiply with C, right? If you take C out of this logarithm, because C is constant to ZG, the integral will be simply C, right? It has nothing to do with ZG. Then the benefit is that, okay, if we put a normalizer here, then the denominator becomes a valid distribution. And we know that only when your QZG to be equal to this distribution in the denominator, you minimize the KL divergence. In other words, you maximize the evidence lower bound. Right. So now we get our updating rule, right? So our QZG will be proportional to this exponential of, you can see that expectation of the log joint probability under QZ not G. And of course, you need to compute the normalizer, which is by integral out this exponential term of ZG. So this is how we get the mean field update. Right? So you can see that every time we just pick one QZJ to update, fix all the other QZIs, right? And then our updating rule is that, okay, I'm gonna look at the distribution which is proportional to expectation of the log joint probability under the approximate posterior of all the other variables. Then you normalize it. You take exponential, normalize it. You got QZG update. Then you switch to another QZG and then do the same thing. Just do this cyclically until convergence. Any questions so far? Okay. So here's the algorithm framework for the in-field variation inference, right? So first, we're going to choose a factorized posterior form as our approximation family, right? QZ equals to a product of QZIs where the i's are not overlapping, right? And then we repeat the following procedure, right? In each iteration, we go through every sub variable ZJ, we fix all the other sub variables and then only update QZJ using this mean field updating rule. And then you switch to the next sub variable, ZG plus 1. You do the same thing. Just go through every sub variables. You update every QZJs your posterior form. You finish one iteration, then you conduct next iteration. You do this until the change of QZGs are less than some tolerance level or some maximum number of iterations are done. This is called mean field variation inference. Any question regarding the algorithm framework? Okay, great. So now let us look at some concrete example to apply the mean field variation inference. Right? By the way, mean field word is coming from physics. So this technique is not invented by computer scientists. It's invented by researchers in physics. Right? And they want to ask me some posterior distribution in stochastic physics. Invent this idea. It's a brilliant idea. So we're going to talk about the application of mean field variation inference in this linear regression, Bayesian linear regression model. Right? So we actually mentioned this model before. So first, we're going to assume our width vector W is sampled from some Gaussian prior with mean 0. And prior variance is alpha inverse I. Alpha is some kind of latent random variable, which it is sampled from a gamma prior. Like, as we mentioned that the gamma prior is conjugate to a Gaussian distribution, right? If the alpha is used as the inverse variance of a Gaussian distribution. Right? So, and here A0 and B0 are fixed constant. We're assuming that they're known, right? And then given the W, right, we use Gaussian likelihood to model a set of n data points, right? That means each output Tn is assumed to be sampled from a Gaussian likelihood, where mean is the inner product between the width vector W and feature vector Phi, and the variance of the Gaussian likelihood is beta inverse. And here we assume beta is fixed and known. Right? We're not trying to estimate posterior of the beta. Right? But later we see that even if you want to do that, it is feasible and straightforward to extend our discussion. And now we can write down our drawing distribution over alpha, over W, and over data T, which is prior of alpha, which is gamma distribution, and the Gaussian prior over W given alpha, and the Gaussian likelihood over T given W, right? And then our task, right? Our goal is to estimate the posterior distribution of W and alpha given the observation T. So remember previously we just assumed alpha fixed, right? If alpha is fixed, then the posterior distribution of W given T is very easy. It's just Gaussian. But now, if you want to join and estimate the posterior distribution for W and alpha, unfortunately, it is intractable. You won't be able to compute that. And you can try that. I encourage you to verify that. So then, what is our how do we do, right? We can now compute the exact posterior of this W and alpha given the data T, right? So we're going to use the mean field variation inference. Right? And here we assume the approximate distribution of the posterior of W and alpha is factorized as posterior of W times posterior of alpha. So, of course, this factorized assumption implies that we assume in the posterior distribution, our approximate posterior distribution W and alpha are independent. But I have to point out this is not true in most cases. Right? So we just want to use a simpler form of approximation to capture the information, capture some information from the true posterior. And then let's see, how do we conduct the mean field variational update to optimize QW and Q alpha. So this is relatively straightforward. You just apply the mean field updating rule we just discussed, right? So update Q of alpha, we fix Q of W, right? And then we need to compute the expectation of the log joint probability under QW only. Okay? Then you take exponential and you normalize it, you get your Q alpha. And you find that this Q alpha is a gamma distribution. It's a gamma distribution. Of course, the parameter of the gamma distribution is related to the dimension of W and also the expectation of W transpose W under QW. I will leave it an exercise for you to figure out the details, right? But it is relatively straightforward. And similarly, when we want to update Q of W, we need to fix Q alpha, right? We need to fix Q alpha, and we need to take the expectation of a log joint probability under Q alpha, and then take exponential and see if we can get the updated posterior distribution, right? Posterior approximation, which turns out to be a Gaussian distribution. And this is the updating rule. But again, your updated form of QW needs to incorporate some information from Q of alpha. You can see that from here, right? Where you have to, your covariance matrix has to leverage the expectation of alpha under Q alpha. So again, I want everyone to try to figure this out yourself, right? But I can give a little bit hint, right? If you decompose this joint distribution, right, it is P of alpha, P of W given alpha, and P of T given W, right? So you can see that we will take a logarithm P of alpha, it is constant to W, so you can throw them out, right? And you only need to look at the expectation of log terms that relate to W. And then we will take a logarithm this and logarithm this is a logarithm two Gaussians, right? And we put them together, you find that, okay, it is essentially just a combination of the first order term regarding W and the second order term regarding W. You take exponential again, according to the square completion trick we discussed before, it must be a Gaussian. That's how we get this Gaussian form update of the QW. Does it make sense? Any questions so far? So we can see that during the whole mean field variation update, right? Every time when we update Q of W, we do need some expectation of of alpha on the Q alpha, and during the update of Q alpha, you need some expectation for W under QW, right? So you do this alternating update, you update both Q alpha and QW in an iterative way, right? So once you have obtained this variational approximation of the joint distribution of W and alpha with the usage, right? We can plug it into our predicted distribution. Right? So according to the definition of predicted distribution, you're gonna need some marginal distribution of the posterior W given the data T, and then multiply with the likelihood, right? And then you marginalize out W. Right? But here, because this guy is analytically intractable, why? Because you don't know what is the exact distribution of W and alpha given T, right? You don't know this, of course you won't be able to know the marginal posterior distribution of W given T, right? But here, according to the mean field variation inference, in our approximate distribution, we know that this guy is simply Q of W, right? Then you just shove your approximate Q of W into this integral, you can get your predicted distribution, which is still a Gaussian distribution. Okay. Any question before we proceed to a more general case of mean field variation inference? Okay, so we can extend this to more general exponential family. So in general, if your prior distribution of the latent random variable eta is conjugate to the likelihood, then the mean field variation inference variation update guarantee you to give you a closed form update, and the update form is also in exponential family. So suppose this is our model, right? You get some latent random variable eta, right? And which is sampled from some prior, right? And then you have your Z and X, right? X are observation, right? Together, sampled from a exponential family likelihood, right? So if we can recall, the prior of eta is conjugate to the exponential family likelihood, right? This is a general conjugate form to this exponential family likelihood. And here in the data, right? In the data part, we assume, okay, you got n data points, right? So you got x and z n here, right? And your likelihood has this general exponential form. You know, this some h function x and z n, and g eta times this exponential form. The eta is natural parameter, right? And you have this sufficient statistics, which is function of both x and z n. Then our goal is to estimate the posterior distribution of a times z given the data x. And here we assume the mean field variational form. Right? We assume the posterior of z and eta can be approximated by q of z or a times q of eta. And then we can apply the mean field variational updating rule we just discussed to this general form, right? So you can update QZN, right? QZN is proportional to exponential logarithm of the joint probability, right? And you have to, you have to take an expectation over eta and logarithm of the joint probability, right? And if you look at logarithm joint probability, it contains the prior of eta and the likelihood, right? And prior of eta actually doesn't contain z at all. This is constant to z. So you can just throw them out because during normalization, they're just cancel, right? So what you need to do is just to take a logarithm over the likelihood and then take expectation under eta, right? So this guy becomes, let me write more clearly. Okay. So you got log P of eta times log P of X and Z given eta, right? As we just mentioned, P of eta doesn't contain Zn at all, right? So it's just constant. You can just throw away because this is x proportional, right? If we will do the normalization, normalization, it will contain log P eta as well. So they're gonna be canceled out. So this is actually exponential to proportional to exponential of the expectation of Q eta times the log likelihood that contains Zn only, which will be the n state point, right? Because only this likelihood contains Zn, all the other likelihood doesn't contain Zn, right? If you look at here, right? And then the remaining thing is pretty straightforward, right? If we take a logarithm, right, G eta is kind of constant to Zn, you just throw them out, right? You just need to take a logarithm of this guy, right? Take a logarithm of this guy is log h x and Zn, right? It is constant to eta plus log J eta plus log exp is cancelled eta transpose u x and Zn, right? You take expectation over q eta under this logarithm, right? And this guy, these two guys are, because this guy has nothing to do with Zn, you can just throw them out. And this guy doesn't contain eta, it's constant, right? You only need to take expectation over this linear term to eta, which is just the expectation of eta transpose u x and Zn, right? Then you take exponential, you normalize it, it will give you this. It is still an exponential family distribution, right? Does it make sense? I mean, it's totally fine if you feel like some details you do not capture, it's totally fine, because I would just want to give you the thread how we arrive at there, and you can just practice by yourself to show that. David. Z is some kind of random variable associated with every data point xn. Let me think about one case. Yeah, maybe you got a Gaussian distribution, right? You just know part of the variable. Like, this is your Zn, this is your Xn. But you know there are Z and Xn are joined some Gaussian, right? But unfortunately, just measure part of it. And then you can infer that. Right? Or other, this can be some well, it's not appropriate to say it's categorical variable, but because categorical variable, Z and Xn could be D might only be 0. Yeah, let us just assume this is a Gaussian, right? And only part of these Gaussian variables are observed. And how do you infer the other part? Yeah, or some other like V-sharp distribution, you only observe part of this matrix. It's pretty common. Right? If you observe, like, you're supposed to observe the whole matrix, right? But what if you just observe part of it? You just observe this part and this part. How do you estimate the hidden matrix entries? Right? So then you do this very mean field update. You got your form, right? And remember this G function essentially is a normalizer, right? I mentioned is because it's exponential family, so the normalizer must be a function of natural parameter, right? So in a variation update, natural parameter becomes the expectation of the eta, right? So that's why the normalizer will becomes a function of the expectation. Does it make sense? Right. And then you can follow the same rule to update the Q of eta, right? Given QZN, all QZNs, and then this will give you the same form as in the prior, but of course the parameters is changed. Right? So again, I will ask everyone to derive those stuffs by yourself. Any questions so far? Okay, great. So we have finished the introduction of the global variation inference. And next, we're going to introduce the local variation inference. So global variation inference, as we mentioned, like we want to minimize the Carroll divergence, right? We want to introduce the third distribution, which we call approximate posterior, to maximize the variational evidence lower bound, right? We do not make any approximation to the joint probability itself. That's why it's called global variation inference, right? We maintain the whole joint distribution. But local variation inference takes another strategy. So it assumes that, okay, what if the global, the variation evidence lower bound is also very difficult to optimize? Right? For example, in general, you can write your joint distribution like X and Z, maybe written as some right, a product factors, right? And we know that this is the global variation inference, right? Px z given q of z, something like that, right? So sometimes even maximizing this guy is very hard, right? Partly because some factors or many factors in this joint distribution is tricky, it's complex, making this whole optimization difficult. Right? Then an additional idea is that, okay, why not we introduce some approximation to these tricky factors? Like we're going to use some simpler form to approximate those factors in the joint distribution and then maximize the approximate evidence lower bound. So this is called local variation inference. Right? And usually we're going to seek a bound, or rather than just give some arbitrary approximation, we seek a bound over the factor function in a joint distribution such that I can construct another lower bound of the variation evidence lower bound. So the relationship is like, okay, I got my original evidence lower bound is a lower bound of the log mod evidence, right? Is a mod evidence, right? And through this local variation inference, I'm construct the further lower bound, right? Something like that, right? Is upper bounded by this evidence lower bound, and so it is also upper bounded by the log of the mod evidence. So there are a variety of ways of constructing such a bound, right? A common use trick is to use the convex conjugate to construct such a bound. And let us just a quick review what is convex conjugate, right? We discussed it at the very beginning of this semester, right? So really, if you've got function, convex function fx, right? We can represent this convex function as some maximum of a linear function regarding x, right? Okay. For any x, you can, this guy corresponds to, right, this is fx, right? So this guy corresponds to some tangent line of this convex function, right? And you can show that for any value x, right, it can be represented as the upper bound of this linear function to x. And how do you get the intercept of this linear function, which is g of eta? We're going to solve a dual maximization problem. Right? That's how we define the convex conjugate. Right? So the idea is that, okay, if I got some factor which is convex, right? Here is convex, then I'm going to use a convex conjugate, right? I'm going to replace this factor in my probability distribution by its lower bound. And what's the benefit of that? So you can see that in this lower bound, regarding x, it is just a linear term. It's just some lambda times x subtracted by some function only determined by lambda. So that means when I replace fx with this lower bound, the terms related to x becomes much, much simpler. It's just a linear term. And in this case, and then under that circumstances, we maximize the whole new lower bound and usually make the estimation regarding the posterior distribution of x much, much easier. So that's the idea. And of course, introducing this additional lower bound to the original probability factor will introduce additional parameter lambda, right? If you want to tighten the bound, you also want to optimize lambda, right? To make this lower bound to be close to fx as much as possible, right? As close as possible. So you need to optimize the additional parameter lambda as well, right? So of course there's no free lunch. So, and this lambda is called variational parameter, because why? It is introduced additional parameter to tighten the bound. So this is a general idea, right? So to say it more concretely, right? So suppose in general we got this joint distribution, theta is a random variable, x are data, right? So the log joint probability can be written as log prior plus summation of log likelihood over every data point xn, right? Given theta, right? If this log likelihood is complicated, but it is convex to the latent random variable theta, right? We can seek for some convex lower bound to f theta, right? To this guy, right? And then replace this log likelihood by some linear function of theta only. And then we merge all those terms together to do some posterior computation. Of course, you can see that because it's just a linear term, right? If you take exponential, it's just the exponential family. So your update of the q theta is often much easier, right? And then you need to optimize lambda, right? You want this lambda to make your bond to be as tight as possible, right? In the ideal case, it will be exactly the same as f theta. Later we'll see it won't be possible in practice. But anyway, I want to optimize lambda to tighten the bond. So I need to optimize this additional variational parameters lambda. Any questions so far before we proceed to a concrete case of this local variation inference? Does the whole idea make sense? Okay. So now we're gonna apply this local variation inference approach to the Bayesian logistic regression model. So if you could recall, right? Our Bayesian logistic regression model is like something like this, right? I got a prior or my W, right, or my weight vector W, and suppose I get my n labels, right, which are binary labels, right? So each likelihood will be Bernoulli likelihood, right? And Bernoulli likelihood will be W transpose the feature vector to the power of say Zn is the label, either 0 or either 0 or 1, right? So you got this logistic function in the Bernoulli likelihood. So when you compute the posterior distribution of W given the data Z, let me avoid using Z, right? Let me use T, right? So each label is Tn, right? It is very hard, right? There's no way to compute the exact posterior distribution. Even if you try to maximize the variational evidence lower bound, you won't be able to exactly to conduct direct optimization. How to address this problem, right? Our idea is that because the bottleneck is the sigma function, right? So you want to construct some kind of lower bound regarding sigma function, but not exactly sigma function, right? so that I can replace sigma function by other easier form. Then I do the variational update of QW and make it much easier. That's the idea. Right? So now let's see how do we fulfill this strategy. So first, we want to observe what is the property of the sigma function. Right? So the first observation is that the log sigma function is concave. How do we see this? Right? We just check the derivative and second order derivative. Right? So if we take logarithm of the sigma function, right? What's it? Yeah, someone just give me the answer, but let's just do a little bit derivation. Right? So according to the chain rule, it will be 1 over sigmoid and sigma prime, right? And we mentioned that sigma prime equals to sigma times 1 minus sigma, right? So which is only 1 minus sigma, right? So if you want to check it is convexity or concavity, right? We need to take the second order derivative. So if we take second order derivative, right? You just take derivative over this 1 minus sigma again, right? Just recite the result is minus sigma times 1 minus sigma, right? So this must be a non-positive, right? Why? Because sigma is non-negative, 1 minus sigma is non-negative, the product is non-negative, and negative of them is non-positive, right? So that means this guy is concave, right? If the second order derivative is non-positive, non-negative, then it is convex, right? It's non-positive, it's concave. Does it make sense? Right? So just keep this on your mind, right? So then we want to look at this log sigmoid function, right? Because when you take logarithm over your Bernoulli likelihood, right? You see that you have some log sigmoid term, and that's why we are interested in the property of log sigmoid function, right? So if you look at the form of log sigmoid, right? Take a logarithm over here, you you want to put this denominator up, right? So you put minus sign in front of it, and you do some kind of arrangement, right? You take some common term, e to the power of minus half x outside and move it out of the log, right? So here's your result, right? Your log sigmoid equals to half x subtracted by this function, right? Log e to the power of half x plus e to the power of minus half x. This is your f of x function. And this term has already been linear function to x, right? So we can just put it aside. We just look at the fx itself. Fx is minus logarithm e to the power of half x plus e to the power of minus half x, and we found that interestingly it's a symmetric function, right? Right. And fx is equal to f minus x. So that means because it's symmetric, that means fx is the same as you put the absolute value of x into f, right? It's the same, right? In other words, it is equal to, you take square of x and take square root. Let's give you the absolute value of x and into f, right? So why would they take this view? Because then we can view x squared as your function. You can view this as a function like of x squared only, right? Like for better to avoid like notation confusion, like we can view it as a function of x squared only, right? This new function can be viewed as a f bar, right? So I means I can view f of x as another function of x squared. Right? And what's the benefit? We can show that if you view the original f function of x as a function of x squared, this new function f bar is convex to x squared. Then we can apply convex conjugate. Right? we can apply convex conjugate. That means my F bar X squared can be written as lambda squared subtracted by G lambda. Okay. And how do we get G lambda according to the convex duality? Your G lambda is obtained by maximizing lambda X squared subtracted by your F bar function. So this is just a straightforward application of the convex conjugate. So now, we want to see that how can we get this G lambda, right? We know that it is a maximization of this lambda X squared subtracted by the F function, right? If you view it as a function of X squared, right? If you take the derivative with respect to X squared, and you set derivative to be 0, you get this G of lambda, and you find that G of lambda, you find that you have this relationship between lambda and X. In other words, for any lambda, you have to solve this equation to get X, right? To get X and X squared, you got G lambda value. So let us assume the optimal value X, which satisfies this equation, we denoted by Cauchy. So then we can represent lambda in terms of Cauchy, which is just minus 1/4 Cauchy tan H gamma over 2, right? And it can be written this way, right? This is just the definition of tan H. So don't worry, don't get scared about this details. It's just tedious derivations, nothing special. You can practice by yourself. You can replicate them by yourself, totally, right? I'm just talking about this thread, right? So, and also from the form of lambda, we can see that this lambda is also symmetric to Cauchy. Right? So for some lambda, if you get Cauchy, and for other lambda, you get minus Cauchy, and these two lambdas will be the same. So now we're going to represent lambda in terms of Cauchy. And then we construct this convex conjugate, right? So we got G lambda, right, equals to lambda Cauchy times Cauchy squared, right? Remember, it's a maximize of this, right? And optimal X, the optimal X is Cauchy. So I just replace X by the optimal X, which is Cauchy. That's where I get my G lambda, which is lambda Cauchy times Cauchy squared subtracted by F Cauchy, which has this form. Right? And then, given the G lambda, I can construct a lower bound of my Fx, right? Remember, Fx is Fx is here, right? This is minus log e to the power of half x plus e to the power of minus half x, right? So I get a lower bound of this Fx, which has this form. Lambda x squared subtracted by lambda c squared subtracted by logarithm e to the power of half Cauchy plus e to the power of minus half Cauchy, right? And then because our log sigmoid function, as we derived before, is half x plus fx, right? And then I got my lower bound of log sigmoid function is this guy plus half x, right? Then if you just take exponential on two sides, right, you got your lower bound of sigmoid function, which is here, right, which is here. Okay. You got the sigmoid function of Cauchy times exponential. The exponent is x minus Cauchy over 2 plus lambda Cauchy times x squared subtracted by Cauchy squared. This is just a straightforward by taking exponential over this guy, right, and this guy. Right? So now we have constructed a lower bound of the sigmoid function. Does this whole procedure make sense? Okay. Any questions so far? I'm just talking about the whole steps, right? I'm not saying like we should sit down together and look at every step. I just give you the lead, like how we apply the convex conjugate to arrive at a step. Does it make sense? Okay, so then here is just one example, right? So this is your sigmoid function, and for particular, of course, the lower bound is up to different choice of Psi, right? If you choose one Psi to be 0.25, this is what this blue curve gives you the lower bound. And if you choose a different Psi value, is 3.0, then the curve, the blue curve will change, but it will guarantee to be always below this sigmoid function. And then let us go back to look at the likelihood of our Bayesian logistic model, right? So as we mentioned before, right, our likelihood for any data point t, right, and given the feature vector t is a Bernoulli likelihood where the probability of the sigmoid function, where the input to the sigmoid function is this score, right, W transpose phi, the inner product between the V vector and the feature vector. And if you do some kind of like several merging, right, so you can see that the likelihood can be written as e to the power of a, which is W transpose phi, times sigmoid of minus W transpose phi, right? And remember, we just got a general lower bound of sigmoid function is bigger than a bunch of those guys, right? So now we can just shove our lower bound, right? This from our previous results, right? And where lambda Psi is represented by Psi, right? So now we can get a lower bound of the likelihood for every data point we observe, right? Which is e to the power of at times the lower bound of sigmoid minus a. So here this lower bound essentially is just to replace z here by minus a. Okay. Right. Again, this is a little bit tedious, but it's straightforward. Right. Now, if we replace every data likelihood, right, P of Tn given W by the lower bound, like for every data point, say for every data point Tn, I'm going to introduce a variational parameter Cn, right, to construct such a lower bound, right? And then we can represent, or we can obtain a lower bound of our joint probability. So our joint probability is the Gaussian prior over W, and the likelihood of every data point given W, right? And likelihood every data point of likelihood is lower bounded by this guy, right? So then we get a lower bound of the joint probability, which is P of W times this HW Csi, right? So remember this Csi is bolded. That means it contains n different, big and different variational parameters, right? For data point n, we got Csi n. Right? So again, this is lower bound is a product over every data point n. Does it make sense? Right? So it looks like we are going through a kind of like complex steps to arrive at here, right? So what's the benefit? If you just look at lower bound and prior, right? This guy is a Gaussian, right? Maybe something like that, right? Like alpha times I, something like this, right? This is a Gaussian. And now if you look at in the lower bound, what are the terms related to W? It's just some linear term related to W and square term related to W, right? If you expand them, just some quadratic term related to W. This looks like Gaussian. So you have a prior is Gaussian. In your lower bound of likelihood, all the terms related to W will give you a Gaussian as well. So to put them together, if you normalize only over the prior and the lower bound, it will be a Gaussian form of the posterior W. So this is a benefit. So now let's go back to our global variation inference, right? So the global variation inference is that, okay, I'm gonna maximize this evidence lower bound, which is expectation of log fraction between the joint distribution and approximate posterior distribution, right? Which is equivalent to minimizing the KL divergence between the approximation and the exact posterior, right? So the problem is that, okay, this joint, even for maximizing this lower bound, is computationally infeasible or it's too difficult. How can we do that? So our idea is that, okay, I'm gonna introduce a lower bound of my likelihood, right? I construct a lower bound of the joint probability. Now I'm gonna replace my joint probability in the evidence lower bound by this lower bound of the joint probability. And then I maximize the new lower bound, right? With respect to the approximate posterior distribution Q of W. And we find that if we doing this, our QW is very easy to optimize and to give you the exact form, which is Gaussian distribution. And it's fairly easy to see this because if you take the logarithm of P of W and logarithm of this lower bound term, you will find that you will have only the terms related to W will only be some linear terms like A transpose W and quadratic terms like W transpose B, W, something like this, right? If you got all those terms together by leveraging the square completion trick we discussed previously, you can immediately get that your QW, which maximizes this new lower bound, will be a Gaussian. This is the form. Again, I will request everyone to derive this form by yourself. It's tedious, but it's straightforward. Right? But the problem is that this is now done, right? We know the optimal form of QW, right? Given this new evidence lower bound will be a Gaussian, right? But we have yet identified the variational parameters C, right? As we mentioned, right? We replace the joint distribution by its lower bound. Of course, we want this bound to be as tight as possible, right? So that means that we also need to maximize this new lower bound with respect to the variational parameters for Cs. Okay. If you maximize this new evidence lower bound with respect to C, right? And again, you take logarithm and you take expectation with respect to Q of W, you set the gradient to be 0, it will give you the optimal to C given current QW with the following form. Right? Again, it is tedious, but relatively straightforward. Right? So now these two steps gives us an alternating update procedure, right? Given the current QC, I'm gonna use this form, which is Gaussian, to get my optimal Q of W, right? And then fix Q of W, I can obtain my optimal variational parameters for C to maximize the new evidence lower bound, right? And then I fix my C and update my QW, and then I fix my QW and update my C. So we just do this cycling updates. Does this make sense? So actually, in this way, we obtain a new version of EM algorithm. Right? So you can see that the alternating update of the QW and the variational parameter to C actually form these two steps, right? The updating of Q of W given C fixed, we call it E step, right? And then given the approximate posterior QW fixed, and the updating of these variational parameters to C, we call it M step. So this procedure is called a variational EM algorithm. It's not true EM algorithm because true EM algorithm, you're computing the exact posterior, right, under the current model parameter. But here, it's not exact posterior at all because you're even changing the form of the joint probability. you replace it by a lower bound. Any questions so far? Okay, so this new lower bound is often referred to a variational lower bound. Why it is called a variational lower bound? Because we introduce an additional set of parameters. You see here, right? And this is actually just a bound to. It's not only bound to the original model evidence. It's also bound to the original distribution, joint probability, right? And in theory, if the family of Pessit, right, number of Pessit choose to be like arbitrary many, and Pessit to be after accuracy, this lower bound can reach the original joint probability. Okay. Remember, our convex conjugate, right? We know that there will be some places. There will be some particular choice of here lambda here to make your lower bound to be exactly the same as your original function, right? But in the variational inference, this is usually infeasible, right? Right. If you do not restrict the range of the variational parameters, they have some setting to reach the equality. But because you make some simplification, you make some constraint of the variational parameters, usually you will never be able to reach the equality. Right? If we take the example here to illustrate, right? So we know that this is a sigmoid function minus W transpose phi is lower bounded by some W and C, right? So in theory, right, for any input value to this sigmoid function, you have some C value to make this inequality becomes equal, right? But here the problem is here, right? W here is not fixed value. W is random variable. So W can take every possible value, right? But just with different probabilities. Then the problem is that if you want to make it equal for every W, your C should vary with W as well, right? But our problem is that we won't be able to use an infinite number of C. That's too many. We cannot optimize C in that way, right? So in fact, is that for every data point, right? So here is phi n, right? We only choose one single point of C to approximate or to lower bound this function, right? For every possible W. So actually, this lower bound cannot ensure that okay, it was equal to the sigma function for every possible choice of W. Right? Actually, in most of the cases of W, it will always be less than the lower bound, less than the sigma function. So now we can see this trade-off, right? So ideally, if you can introduce enough large number of the C values, you are able to make the lower bound to be equal to the original factor, right? But here, this is too costly, right? I cannot introduce a different C for every possible W. I can only introduce one C value, right, for every data point n, which is definitely not enough to ensure the equality in all the cases. That's why, in practice, in the variational inference, to trade off to the efficiency, we have to sacrifice some accuracy. So I think the last 10 seconds I want to talk about is called variational EM algorithm, which not only including updating the variational parameters to C, but also if your model itself contains some hyperparameters theta, in the M step, you can also maximize your lower bound with respect to theta. You can do it all together. Like in the E step, given theta and given the current variational parameters, you compute your approximate posterior, right? In whichever form you choose, right? In M step, you maximize the evidence lower bound both in theta and also the variational parameters together. So this is a more general frame called variational EM algorithm. Okay, so let's stop here today, right? So on next Tuesday, we're going to wrap up variational inference framework and we'll proceed to the next type of approximate inference approach. It's called Markov chain modified or something.